So welcome to the video. Today we're going to take a look at how to do multiple linear regression on version 31 of SPSS. So we will most commonly use this analysis when we have two or more predictor continuous variables and we have one continuous dependent variable, and we want to assess whether those predictor variables can predict a significant amount of the variance in the outcome variable. So for this example, we are going to imagine that we're interested in how stressed people are. So we have stress scores in this column here on the right, and we're going to see whether we can predict how stressed people feel based on how many hours they spend on a screen every day, how much physical activity in minutes they have each day, and how many hours of sleep they get each day. So let's start off by looking at how to put these data into SPSS. So we're going to go down to a variable view, and then we're going to give a name to the first of these predictor variables. So let's call the first one screen time, and then the next one we're going to call physical activity. And I'm just using a underscore between these words because I can't use a space in this column. So physical activity is the next one. The next one is sleep. And then we'll give a name to the outcome variable, which is sometimes referred to as the dependent variable. So I'm going to call this one stress. And in this case, we have four continuous variables. So continuous is kind of another word for scale. So we can just use the word scale, or we can choose the scale option in this column here. And then we're ready to put the data in. So we can go down to data view. Then I'm just going to go back to my Excel file and I'll select the top left piece of data. And then I'll go down to the bottom and I'll select the bottom right bit of data while holding Shift. Then I'll go Command or Control C to copy those data. Then I'll select the top left cell in SPSS to paste those data in. So we're now ready to run the analysis, but we just want to check a few assumptions while we do this. So there are a few assumptions of this analysis. So one is that there are linear relationships between the predictor variables and the outcome variable. And I've just put in italics for all of these assumptions how we're going to check them. So for this first assumption, we need to create several scatter plots. But for all of these other assumptions, we can actually just tick a few boxes as we're running the analysis itself. So let's first take a look at how to check this one here. So we're going to create scatter plots that represent the relationships between the predictor variable, or each of the predictor variables, and the outcome variable. So to do this, we can go up to graphs and then down to scatter/dot. We can then go to simple scatter. This is actually the default option, so we don't need to change anything here. Then we can go to define, and then we can transfer our dependent variable or outcome variable to the y-axis box. And then we can transfer one of our predictor variables or independent variables to the x-axis box. And then we're just going to go to OK, and that creates this scatter plot for us. And then we just need to repeat that process for the other predictor variables. So the same thing again, graphs, scatter/dots, define. I'm then going to just switch out this screen time variable for one of these other variables. Then I'll go to OK, that's going to create that scatter plot, and then I'll just do the same thing one more time for the last predictor variable. So we'll remove physical activity and we'll put sleep into the x-axis box, then we'll go to OK, and now we have three scatter plots for each of the three predictor variables. And then if we double click on any of these, we can go up to here in the chart editor window to add fit line at total, and that's essentially going to put a line of best fit through those data points. And this really is what we want to see. We want to see that we have sort of a diagonal band that is well represented by a straight line, either going upwards in this direction or going downwards in this direction. So this supports the assumption that there is a linear relationship between stress and screen time. So the more screen time people have, the more stress people tend to feel. However, for these two graphs down here, we don't see the same sort of thing. We see sort of randomly organized data points for this physical activity and stress graph. And similarly here, we don't really see that upwards diagonal line or that downwards diagonal line that we'd like to see. So really only this graph here supports the assumption. But as this is just a tutorial, I'm going to imagine that all of the graphs look like this, and we'll just continue with running the analysis. So to do this, we're going to go up to Analyze and then down to Regression, then over to Linear. I'm then going to transfer my dependent variable or outcome variable to this dependent box, and then I'll transfer all of these independent or predictor variables to this independence box. I'll then click on this statistics option up here, and I'm going to click descriptives, collinearity diagnostics, and Durbin-Watson. So if we take a look at this assumptions checklist, we can see that one of them is that there is no multi-collinearity. So we're going to get statistics relating to that assumption by ticking the descriptives and the collinearity diagnostics box. And if we look at the checklist again, another assumption is that the residuals are independent, and we're going to get statistics relating to that assumption by ticking the Durbin-Watson option here. So once this looks like this, we can go to continue. Then we're going to go to plots, and we're going to put this Z-resid option in this X-axis box and this Z-pred in this Y-axis box. So that one relates to another of these assumptions. So this relates to the assumption that there is homoscedasticity. Another assumption that we can check while we have this plots option open is this assumption that the residuals are normally distributed, which we're going to check using a normal PP plot. So we're going to click this option here, then we'll go to continue. And then the last assumption that we need to request statistics for is this one here, that there are no influential cases biasing the model. And to check this, we're going to generate Cook's values. So to request these, we can go to save, and then we just tick this Cook's option here, then we go to continue, and then we can go to OK to run the analysis. So if we look at this again, we can see that for this assumption that there is no multi-collinearity, we want to have correlation coefficients for the predictive variables that are closer to 0 than 0.8 or minus 0.8. So essentially this assumption is about not wanting our predictor variables to be too strongly correlated with each other. So if we look at this table here, we can see that we have screen time in this row. So this is one of our predictor variables. And then we have its relationship to physical activity here and its relationship to sleep here. And we can see that in both cases we have values that are closer to 0 than 0.8 or minus 0.8. So those relate to the relationship between screen time and physical activity and screen time and sleep. So now we just need to look at screen time and sleep. And again, here we can see that we have a coefficient that is closer to 0 than 0.8. So these statistics here suggest that this assumption of no multi-collinearity has been met. However, we can also look at these tolerance and VIF values that are generated as well. So if we go down slightly, we can find these here in this coefficients table. And what we want to see is that we have tolerance values above 0.2 and VIF values below 10. So here we can see that all of these tolerance values are above 0.2 and all of these VIF values are below 10. So these statistics here also support the assumption that the predictive variables aren't too strongly related to each other. So the next assumption that we can check is that the residuals are independent, and for this we're going to look at the Durbin-Watson value and check that it's between 1 and 3. So we have this Durbin-Watson value here in this model summary table and in this Durbin-Watson column, where we can see that we have a value of 2.109. So as that's between 1 and 3, it's in line with the assumption that the residuals are independent. So the next assumption we can check is that there is homoscedasticity, and as I've mentioned here, we're going to check one of the plots to investigate this assumption. So what we want to see is that the dots in this are basically spread out in a sort of random manner. What we'd like to see is just like a big band of dots. What we actually see here is that we have a bit of a pattern going on. You could arguably say there's a bit of a funnel or a triangle shape, which is not what you want to see. However, for the sake of this example, I'm just going to say it's fine, and we're going to continue on to the next assumption. So next we have the assumption that the residuals are normally distributed, and we're going to check the normal PP plot for this one. So that's this plot that we have slightly above, and what you want to see for this one is that the data points follow the line quite closely. So I think in this case you could argue that they do, which supports this assumption. So I think that one has been met. And then finally we have this assumption that there are no influential cases biasing the model, And for this one, we're looking at the cooks values. So these are actually added to our data file. So we have this new variable here. And what we want to see is that we don't have any values above 1 in this column. If you don't have many participants, this is quite easy to check just by looking at this column. However, if you have a lot of participants, it might be quite difficult. So in that case, you might want to go up to Analyze and then down to Descriptives and then across to Descriptives. And then you could transfer this cooks distance variable into this variables box. And then you can just go to OK, and that's going to produce this descriptive statistics table. And we can see that the maximum value in this column is 0.13. Obviously that's below 1, which suggests that this assumption that no influential cases are biasing the model has been met. So that's essentially how we check those assumptions. We'll take a look later at how we can report those as well. But for now, let's take a look at how we can interpret the results of the regression analysis itself. So the first thing I'm going to look at is this ANOVA table and add this sig value here. And we can see that this sig value or p-value is less than 0.05. It's actually less than 0.001. So that indicates that the model predicts a significant amount of the variance in the outcome variable. And if we look at this model summary table, we can actually determine how much of the variance is predicted by the model. So if we look at this R-square value, we can see that we have a value of 0.67. And if we just move this decimal point over 2 places to the right, we get 67. So based on this, we can actually say that the model explains 67% of the variance in the outcome variable. So we know that the model overall is significant, but now we can also take a look at whether the individual predictors within that model make a significant contribution to it. So to do this, we can go down to this coefficients table, and let's take a look first at this screen time row. And if we go over to the sig column, we can see that we have a value of less than 0.001. As this is less than 0.05, it suggests that screen time significantly contributes to the predictive power of the model. Similarly, for physical activity, we have a value below 0.05, so that contributes significantly to the model too. And finally, for sleep, we have the same thing. We have a value of 0.012. Again, this is less than 0.05, indicating that sleep also significantly contributes to the predictive power of the model. Another interesting column in this table is this unstandardized B column. For example, here we see that screen time has a positive value, indicating that as screen time increases, we tend to see an increase in stress as well. For physical activity, we see that we have a negative value, indicating that higher levels of physical activity tend to be associated with lower levels of stress. And similarly for sleep, we can see that we have another negative value, suggesting that the more people sleep, the less stressed they tend to feel. So that's essentially how we interpret the results of the multiple linear regression analysis. But let's take a look now at how we can report those, as well as the assumptions that we checked before. So we've started off referring to the scatter plots that we created towards the beginning, and I've said that scatter plots indicated that there were linear relationships between the predictive variables and the outcome variable, and then I've just referred to an appendix based on the assumption that I would include those 3 scatter plots that we created within an appendix. Next, I've said to ensure that there was no multi-collinearity, Pearson correlation coefficients were calculated to examine the relationships between the predictors. And I've said that the coefficients for screen time and physical activity, screen time and sleep, and physical activity and sleep suggested that the assumption of multi-collinearity was not violated. So that's based on the fact that all of these values here are closer to 0 than 0.8 or minus 0.8. And just to recap, we got those values from here. So for example, we can see that the relationship between screen time and physical activity has a Pearson correlation coefficient of minus 0.02 if we round that to 2 decimal places. So if we're looking at screen time and physical activity, that's what we have here. And then we've got minus 0.12 for screen time and sleep, and that's what we have here. And then finally we have a value of minus 0.09 for physical activity and sleep, and that's what we have here. Next, I've said, moreover, tolerance values were 0.99 for screen time, 0.99 for physical activity, and 0.98 for sleep. And variance inflation factor values, that's VIF, were 1.02 screen time, 1.01 for physical activity, and 1.02 for sleep, supporting this assumption. So just to recall where we got those from, those are coming from this coefficients table and from this tolerance and VIF column. So for example, screen time, the tolerance value is 0.99 if we round that to 2 decimal places, and that's what we see here. And the variance inflation factor value for screen time is 1.02, and that's what we have here if we just round this value here to 2 decimal places. And then of course I've just done the same thing for those other predictive variables. So next I've said that a Durbin-Watson statistic of 2.11 supported the assumption that the values of the residuals are independent, and that's just coming from this model summary table and this Durbin-Watson column where we have a value of 2.11 rounded to 2 decimal places. Next, I've said that a scatterplot was created to assess the assumption that the variance of the residuals was constant, which is known as the assumption of homoscedasticity. And I've said that the plot did not indicate a violation of this assumption, and I've referred to Appendix B based on the assumption that I would be including this graph here as an appendix. Next, I've said that a PP plot was created to assess the assumption that the values of the residuals are normally distributed, and I've said similarly that this plot did not indicate a violation of this assumption, and I've referred to Appendix C there based on the assumption that I would include this figure as an appendix. And then getting to the last assumption, we've said that Cook's distance values were calculated to ensure no influential cases were biasing the model, and have said that all values were below 1, suggesting that no cases were biasing the model. And that's based on the idea that there are no values above 1 in this column here, which we confirmed by generating these descriptive statistics, where we can see that the maximum value in this column is 0.13. So that's all of the assumptions reported. So now we're getting on to reporting the results of the analysis itself. So we've said that the model was significant and that it explained 67% of the variance in the outcome variable. So let's take a look at where all of these numbers in this sentence come from. So we have an F value of 64.97. So that is coming from this ANOVA table and from this F column where we have this value here of 64.97. rounded to 2 decimal places. We also have these degrees of freedom values in this column here where it says DF. So we have a 3 and a 96. And that's what we have in brackets here. Next we have the p-value of less than 0.001, and that's what we have here in the same table and in the SIG column. And the last stats we have in this sentence is this r-squared value of 0.67, which means that 67% of the variance in the outcome variable was explained by the model, and that r-square value is coming from this model summary table and this r-square column here. So that sentence refers to the model itself, and then we can talk about whether or not the individual predictors within that model made a significant contribution to its predictive power. So we've said that all 3 predictive variables contributed significantly to the model, and I've said that increases in screen time were linked to increases in stress. So that relates to the fact that we have this positive value here in the screen time row, and we have this SIG value of less than 0.05, which is why we've used the word significantly here. And then we've said that increases in physical activity and sleep were linked to decreases in stress, and that corresponds to how we have these minus symbols here in these physical activity and sleep rows. And then for each of these predictive variables, we've reported the unstandardized beta value, a t value, and a p value. So let's take a look at this screen time variable, and we can see that we have a b value of 4.48, a t value of 12.97, and a p value of less than 0.001, and that should relate to what we have here. So we have this unstandardized beta value of 4.48. We have this t value of 12.97 rounded to 2 decimal places, and we have the p-value of less than 0.001, which is what we have here in the SIG column. And then we've just reported those same statistics for the physical activity row, and for the sleep row. So that's essentially how you report the results of the multiple linear regression analysis. I just want to show you one more thing, which is that you can actually make specific predictions about the value of the outcome variable if you know someone's scores for your predictor variables. So let's imagine that we have a person who had 5 hours of screen time a day, 5 minutes of physical activity, and 5 hours of sleep. If we know this, we can actually make a specific prediction about their stress score. And so to do this, we are going to take this value here, this constant value. That's the first part of this sum we're doing. So we have a value of minus 1.22. And then we said that this person has 5 hours of screen time. So what we've done is taken this value here, which is 4.48, and we're multiplying that by 5, so 5 hours of screen time. Then we're adding that to minus 0.09 times 5, which is corresponding to 5 minutes of physical activity. And then we're adding to that 5 times minus 1.37, which is what we have here. And we've got the 5 here because this person has 5 hours of sleep. And if we add these all up, we get a value of 13.88. So a person with 5 hours of screen time, 5 minutes of physical activity, and 5 hours of sleep, the model would predict that they have a stress score of 13.88. So that's about it for the multiple linear regression analysis on version 31 of SPSS. I hope that was helpful. If you have any questions, just let me know in the comments and I will try to get back to you. Thank you for watching, and I'll see you next time.